When most people first learn about difference of squares as a method of factoring, they look at it in terms of factoring by pattern. So traditionally we see a squared minus b squared is factored into a minus b, a plus b, which is a fine way of looking at it. But instead of looking at it as factoring by pattern, I want to look at difference of squares in terms of conjugates. Because if you can wrap your head around conjugates, it's a lot easier to go backwards and get the factored form of a difference of squares. So if you remember, conjugates are a set of binomials, for example, x plus 3 and x minus 3, that are exactly the same except for the middle sign, in this case, a positive and a negative. But again, everything else is exactly the same. And the nice thing about conjugates is that when you FOIL out conjugates, the middle terms cancel out. So when I FOIL this out, I get x squared minus 3x plus 3x and minus 9. So the negative 3x, the positive 3x cancel out, and my final answer is x squared minus 9. A telltale sign that you're dealing with conjugates is that when you FOIL, you get a binomial. And notice here how it's a set of two perfect squares and they're subtracted. Difference of squares. My conjugates can get a little bit more complicated. They could look like 2x plus 5, 2x minus 5. And once I learn the pattern, I don't even have to write out the middle two terms. I can just go right to my answer of 4x squared minus 25 because I know that those middle two terms are going to cancel out. So instead of going in this direction where we FOIL, we're going to look at the inverse, which again is factoring, and we're going to look at how can I factor using the pattern of difference of squares by knowing about this idea of conjugates. So for our first example of difference of squares, I want to factor the following quadratic binomial, x squared minus 16. Now I know that if I get a binomial, originally I had conjugates, a plus and a minus. Doesn't matter which one's plus and which one's minus. They could be flip-flopped. So all I need to do now is look and think, how would I get an x squared by multiplying something by itself? In other words, more or less take the square root. X times x gives me x squared. And then how would I get a 16 by multiplying some sort of number by itself? That gives me the plus 4 and the minus 4. I get my set of conjugates that if I were to FOIL them out would take me right back up here. So difference of squares is a lot about recognizing the pattern and making use of that pattern because it gets me my answer in factored form very quickly. Now I could also use the method a equals 1 to factor this, but it would be more work. It's a lot easier if I can just take the difference of squares and recognize that it exists. So that allows me to do these problems really quickly. If I start out with something that looks way more complicated, like 9x squared minus 169. Now I could use a is not equal to 1, but if I used a is not equal to 1, I'd have to deal with numbers like 1,521, and then find numbers that add and subtract and all of that, and I'd just rather not do that. So I noticed that it's going to be a difference of squares. It's a binomial, so that means I started with conjugates, plus and minus. Now I just look through and say, hey, what gives me a 9? Well, that's a 3. What gives me an x squared? Well, that's an x. So I put a 3x and a 3x. Then I look here and say, hey, what times itself gives me 169? And I know that that is going to be 13 and 13. And that's all I have to do in order to get my set of conjugates that FOILed out to 9x squared minus 169. I can take this and I can extend this thinking a little bit to more complicated problems. Something like 25x squared minus 49y squared. Again, I approach this using difference of squares because I have a binomial. And specifically, I have perfect squares. So I get a plus and a minus because they're conjugates. Conjugates FOIL out to a binomial. And then I look and I think, what gives me a 25 and what gives me an x squared when I multiply itself? That's going to be a 5 and an x and a 5 and an x. And then again, I look at the 49y squared. I don't care that there's a y squared there. I just follow the same process. The 49 is from a 7. The y squared is from a y. So I put a 7y in both of those places. And if I were to FOIL this out, I would get my binomial above. Last example, a little bit more complicated because now I'm going to go ahead and change the exponents on the variables. I get 100x to the 4th minus 49y to the 6th. But I don't change my approach. I know that if I had a binomial, once I FOILed, I started out with conjugates, plus and minus. The numbers are the easy part to deal with. The 100, I know I'm going to need tens, so I put my tens. Now x to the 4th, I remember my exponent rules, and if I multiply x squared and x squared, I add the exponents, and that would give me x to the 4th. For the second piece, I just follow the same logic. To get the 49, I need a 7. To get y to the 6th, remember my exponent rules, I need a y to the 3rd and a y to the 3rd, because you add the exponents whenever you multiply the y's together. And that's all there is to it whenever I do this in terms of difference of squares. So instead of thinking of it as a pattern necessary, I like to think of it in terms of conjugates. What conjugates were multiplied together to give me my form that I'm trying to factor?